BERT. Reading in both directions. Part 7. The proof. Experiments and results. In parts 3 through 6, we built up the complete picture of how BERT works. That's the theory. Now comes the proof. Part 7 is where the authors put BERT to the test. They evaluate it on 11 different natural language processing tasks, spanning 4 major benchmarks. And the results aren't just good. They're the kind of results that made the entire field stop and pay attention. By the end of this part, you'll understand what each benchmark actually measures, why the authors chose these specific tasks, and what the numbers tell us about bidirectional pre-training. Let's start with the first benchmark, GLUE, the General Language Understanding Evaluation. A collection of diverse language understanding tasks, packaged together as a single benchmark. The idea is simple. If your model is truly good at understanding language, it should perform well across many different types of problems, not just one. The GLUE benchmark contains 9 tasks. The authors excluded one task, the Winograd Natural Language Inference Dataset, WNLI, because the GLUE organizers themselves flagged construction issues with it, and every submitted system performed worse than the majority class baseline. That leaves 8 tasks in the evaluation. 6 of the tasks test relationships between sentence pairs. Natural language inference in MNLI and RTE, paraphrase detection in QQP and MRPC, question answering as classification in QNLI, and semantic similarity scoring in STSB. The remaining 2 tasks test single-sentence understanding, sentiment classification in SST2, and grammatical acceptability in COLA. Together they cover inference, paraphrase, similarity, sentiment, and grammatical judgment. A genuine spread of language understanding capabilities. Training set sizes range from nearly 400,000 examples for MNLI down to just 2,500 for RTE. That range matters, as we'll see in the results. So how is BERT fine-tuned for GLUE? The fine-tuning setup is remarkably consistent. For every task, BERT takes the final hidden vector of the CLS token as the aggregate representation and feeds it into a single classification layer. A linear projection from H dimensions, 768 for BERT base, 1024 for BERT large, to however many classes the task requires. The only new parameters are those classification weights. The authors fine-tune with a batch size of 32 for 3 epochs, searching over a small set of learning rates and picking whichever works best on the development set. They found that BERT large fine-tuning was sometimes unstable on small datasets, so they ran several random restarts, same pre-trained checkpoint, but different data shuffling and classifier layer initialization, and selected the best model. No elaborate task-specific tuning. No custom architectures per task. Same recipe. Applied 8 times. The results? Both BERT base and BERT large outperform every previous system on every single GLUE task. On the official GLUE leaderboard, BERT large achieves a score of 80.5, compared to OpenAI GPT's 72.8, a 7.7 percentage point absolute improvement. Looking at the paper's own results table, BERT large reaches 82.1 and BERT base reaches 79.6, compared to GPT's 75.1, giving BERT base a 4.5 point advantage and BERT large a 7.0 point advantage. Architecturally, BERT base and GPT are nearly identical apart from attention masking. The paper also notes a few training differences, but the ablations in Part 8 show that most of the gains come from BERT's pre-training objectives and the bidirectionality they enable. On MNLI, with nearly 400,000 training examples, BERT Large hits 86.7 accuracy versus GPT's 82.1. On COLA, with only 8,500 examples, BERT Large scores 60.5 versus GPT's 45.4, a 15-point improvement. On RTE, with only 2,500 examples, BERT Large scores 70.1, up from GPT's 56.0, a 14-point improvement. The pattern is clear. The smaller the training dataset, the larger BERT's advantage. When labeled data is scarce, the quality of pre-trained representations dominates, and bidirectional representations are simply richer. BERT Large also consistently outperforms BERT Base across all tasks, especially those with limited training data. We'll explore why model size matters so much in Part 8. Now, let's move from classification to something more demanding: extractive question answering. And that's where we'll explore the next benchmark: Squad. Squad version 1.1 is a collection of 100,000 question-answer pairs. You're given a question and a Wikipedia passage, and the task is to find the exact span of text that answers the question. This is extractive question answering. The answer is always in the passage, you just need to point to it. This is a token-level task. You're not classifying the whole input. You're making predictions about individual positions. And this is exactly where unidirectional models struggle most. Bidirectional attention lets BERT consider the entire question and the entire passage simultaneously. How does BERT handle Squad? The question and passage are packed into a single sequence, with the question using the A segment embedding and the passage using B. BERT adds two learned vectors, a start vector and an end vector, during fine-tuning. Each token in the passage gets scored for how likely it is to be the start of the answer, and separately for how likely it is to be the end. The answer is the highest scoring valid span, where the end comes after the start. The results are striking. The best previous published single system, BiDAF, the bidirectional attention flow model, with ELMO embeddings, achieved an F1 of 85.8. BERT Large as a single model reaches 90.9 on the development set. With an ensemble of 7 systems and modest data augmentation by first fine-tuning on Trivia QA, before fine-tuning on Squad, BERT achieves a test F1 of 93.2, a 1.5-point improvement over the top leaderboard entry. Even without Trivia QA augmentation, BERT's single model outperforms every existing system by a wide margin. The augmentation adds only 0.1 to 0.4 F1. The vast majority of the improvement comes from the model itself. So that's Squad 1.1. But there's an updated version called Squad 2.0. Squad 2.0 adds a twist. Some questions have no answer in the passage. Now the model must also decide whether any span is a valid answer at all. It needs to say, "I don't know," when appropriate. BERT handles this elegantly. Unanswerable questions are treated as having an answer span at the CLS token position. The model learns to point at CLS when there's no valid answer. During prediction, BERT compares the best non-null span score against the null answer score, and outputs no answer if the null score exceeds the span score by more than a learned threshold. The authors fine-tuned for 2 epochs with a batch size of 48. Notably, Trivia QA data was not used for this task. The results are dramatic. The best score on the Squad 2.0 leaderboard at the time was 78 F1, and the best previously published single model result was 74.4 F1. BERT Large reaches 83.1 F1 on the test set. a 5.1-point jump over the leaderboard best, and an 8.7-point jump over the best published single model. This is perhaps the most impressive result in the paper. Squad 2.0 requires not just finding answers, but knowing when you can't. A much harder judgment. And BERT's bidirectional representations make that judgment significantly more reliable. The final benchmark is SWAG, situations with adversarial generations. This tests grounded common-sense inference. You're given a sentence and 4 possible continuations, and you pick the most plausible one. The other 3 are adversarially generated to be grammatically correct, but implausible. This is challenging because it requires world knowledge, not just language pattern matching. How does BERT handle SWAG? For each example, BERT creates 4 input sequences, 1 per continuation, each concatenating the given sentence with 1 option. A task-specific vector is dotted with each CLS representation to produce a score, and those 4 scores are normalized with a softmax. BERT large reaches 86.3% accuracy on the SWAG test set. The strongest earlier baseline was at 59.2%, and OpenAI GPT scored 78%. That's plus 27.1 points over the earlier baseline and plus 8.3 points over GPT. Expert human performance is 85%, so BERT large edges it. Stepping back, what do the experiments tell us? BERT was tested across 4 very different evaluation settings. GLUE covers 8 diverse NLU tasks. Squad 1.1 tests span extraction. Squad 2.0 adds knowing when no answer exists. SWAG tests common sense reasoning. Across all 11 tasks, BERT achieves state-of-the-art results, not just on a subset, but on everything. The consistent thread is that bidirectional pre-training produces representations that transfer better to downstream tasks, whether those tasks require sentence-level classification, token-level prediction, or multi-sentence reasoning. But knowing that BERT works raises a deeper question. Which parts actually matter? Is it the bidirectionality? The next sentence prediction? The model size? Could you get the same results with a simpler approach? That's what Part 8 is about. The ablation studies, where the authors systematically remove components to understand what's really driving the performance.